In this video, we're going to define angular momentum and talk about some of its properties. So angular momentum, which is symbolized by an L, is defined as the rotational inertia times the angular velocity. So L is equal to I omega. And actually, both of these are vector quantities. So angular momentum is a vector as well as rotational velocity. We previously defined just simply counterclockwise was positive and clockwise was negative, but let's go a step further with this. So you see here in figure B, you have a right hand and a direction of rotation of your fingers here. This is what's known as the right hand rule. If you were to place on a coordinate system, let's say we have a traditional coordinate system with a positive x this way, a positive y up this way, and then the positive z comes out of the screen here. Now if we place our fingers along the x-axis, so you've placed your fingers here, and you curl your fingers towards the y-axis, so place your hand on the screen and curl your fingers towards the y-axis, then your thumb has to point upwards out of the screen. So your thumb points in the direction of the velocity, the rotational velocity vector, which is the same direction as the rotational momentum or the angular momentum vector. And this is why we define a counterclockwise to be in the positive direction, because your thumb points out of the page. If you were to do the same exercise, and you have to use your right hand for this, if you do the same exercise and you place your fingers along the positive y-axis and curl them towards the x-axis like this, so that way you make a clockwise angle, you'd see that your thumb has to point into the screen in order for your fingers to curl this way. So this is what we call the right hand rule, and this really defines what is positive rotation and what is negative rotation. It's really the direction your thumb sticks when you curl that direction, because this stuff automatically becomes three-dimensional. So if we have, like back in figure A here, we have a rotation which is counterclockwise, and so then if I were rotating, if I were to place my hand anywhere on here and turn in the direction of the rotation, my thumb would have to point upward onto the plate, and so, or upward out of the plate, and so this would be the direction of my angular velocity, which is also the same as the direction of my angular momentum. So the angular momentum is the rotational inertia times the rotational velocity. The units of this, so we have the rotational inertia. Remember, I is equal to the sum of all the masses times how far away they are squared. So the units of the rotational inertia are kilogram meters squared, and then for rotational momentum or angular momentum, we then multiply this by angular velocity as well. So your units for the angular momentum are equal to kilogram meters squared times, it's really times radians per second, so we have here times radians per second, but radians are actually a unitless dimension, and so the units of the angular momentum are kilogram meters squared per second. So very similar to linear momentum, which were kilogram meters per second. This is kilogram meters squared per second because of the extra meters we get from squaring the distance when we talk about rotational inertia. And this equation, L equals I omega, is analogous to P equals mv. Just replacing mass with rotational inertia and replacing linear velocity with angular velocity, we have essentially the same equation here, just making the replacements that we've been making all throughout our discussion with rotational motion. So angular momentum is a vector quantity. And if you remember back to linear momentum, in order to change linear momentum, it required an impulse. Remember back that a change in momentum was a force applied over a time, and this change in momentum was called an impulse. If we look at a change in angular momentum, we have change in angular momentum would be a change in I omega. And if we say that our object stays the same as far as its mass distribution stays the same, so that the rotational inertia remains the same, then this becomes a rotational inertia times a change in angular velocity. And if we look instead of just the change in angular momentum, we look at the rate at which it changes. So we divide this by a time. Then we see here we have a change in angular momentum with time would be a rotational inertia times a change in angular velocity with time. But this is a change in angular velocity with time is an angular acceleration. So we have here a change in angular momentum with time is equal to rotational inertia times rotational acceleration, which is what we define to be, well, what we call it a torque. This is Newton's second law for rotational dynamics. So we have a change in angular momentum, very similar to a change in linear momentum, requires a torque to change it. So in order to change angular momentum, a torque must be applied. Remember, in order to change linear momentum, we had to apply a force over a time interval. In order to change angular momentum, we must apply a torque over a time interval. So this goes to explain a lot of phenomena that we actually see in nature. As the rotational velocity, if we come back up here to where we defined rotational momentum or angular momentum, we see it's our rotational inertia times the rotational velocity. As we increase the rotational velocity, we increase this momentum, right? And so this vector becomes larger and larger and larger, right? So we have here, this is our angular momentum vector, and it becomes larger. In order to change it, it's going to require a larger and larger torque. So this is why when you're riding a bicycle, you are much more stable when the wheels are turning than when they're not turning. When the wheels are turning, you have an angular velocity, and so then you have an angular momentum, and it requires a torque in order to turn the bike over side to side. The slower you go, the less angular momentum you have, and the easier it is to change this angular momentum. The faster you go, the more stable you are. This is also explains why a football, if you throw a football, you want to throw it in a spiral so that it goes around in a circle and it continues flying straight. Or it goes around in a spiral, so it's rotating around, so that way, let's draw a picture here. If we have, here's the football, and it's rotating around like this. Then as it rotates around this way, if I were to place my fingers and rotate in that direction, I would see that my angular momentum is in this direction. And so by having that rotation on there, it keeps the football along an axis through its center like this. It keeps it from wobbling around. If I didn't have that spin on it, then the football may rotate like this and be difficult to catch. So this concept is further extended to firing bullets and firing cannons. This is a picture here of a cannon, and you see that there are, so this is a picture of a cannon here, and you see that there are some grooves in this. These grooves are here so that way when the cannon is launched, it spins the shell, the artillery shell or the cannonball around in a circle, so that way it gains some angular momentum and it continues to fly straight like the football down here. This is a concept known as rifling. So rifling is a practice in which you rotate your projectile that you're launching out so that way it continues to fly straight due to the angular momentum that you give it, and having to have a torque in order to change it. We can extend this a little bit. We can extend angular momentum. Say that we have two people with linear velocities, and we want to find out what would be their angular momentum if they were to join together and then start rotating with some angular velocity after. So let's just say here, for the sake of our argument, that they both are moving along at some speed v, okay, and they're moving, opposite directions of each other, but they're both at some speed v here, and they're going to lock hands, and they're going to rotate around this point right here in the middle, same as they are in B. And let's just say they're both equal distance, and we'll call both of their distances r. So when they lock up, there will be some distance r away, so they're both r in this case. Okay. Then we know through our relationships between linear and angular quantities, we know that the linear speed is equal to the radius times angular speed. So we can say the angular speed is equal to v over r. And we also, let's say additionally, that each of them, all of their mass is located at one point, so they're both point masses. So they have some mass of m, and they're located at some distance r away. So the rotational inertia of each of them, and remember this is the sum of all the masses times how far away they are squared, but if there's only the one mass, then this is simply going to be mr squared because they are point masses. This would be the rotational inertia for a point mass. So this is their rotational inertia, and this is their, so rotational inertia is here, and their rotational velocity is here. And we know that we have the angular momentum is equal to I omega. So making these substitutions that we have here, the angular momentum is going to be mr squared times v over r. Having some of these r's cancel out, this is equal to the mass times the distance away times their linear speed. So each of them individually has an angular momentum of mass times how far away they are from where they will rotate, times how fast they are going. This is their angular momentum. So kind of a neat little result. The angular momentum of a point mass. So let's say here, angular momentum of a point mass, which will rotate at some point after it gets stuck and it's locked together, is equal to the mass of that point times how far away it is from where it will rotate times how fast it is traveling. Well, of course, this v is really speed instead of a velocity, because we have to take in consideration which direction is moving, if that angular velocity will be positive or negative. If I were to flip around, so this one will rotate around clockwise, and this one will rotate around clockwise as well. So this omega would be a clockwise omega, which would be negative. But if we were to flip them both around, if we were to say that this person were traveling this way and this one traveling this way, then we would have had an omega like this, which would have been positive. So we still have to pay attention to that for the direction of our angular momentum. So this is really just the speed here. And lastly, I want to talk about the total angular momentum of a system. So very similar to total linear momentum of a system. We have, as I kind of pointed out over here with these two figure skaters, if this the first person has an angular momentum, we'll just say that she has an angular momentum of 2 kilogram meters squared per second, and this is because she is going clockwise, is actually at -2. And then let's say the other person here, it's with a different mass. Let's say she has angular momentum of, say here, -4 kilogram meters squared per second. Then the total angular momentum of the system, if we have these two figure skaters are my system, then the total angular momentum is just the sum of the individual angular momentums. So we'd say here L total in this case would be equal to -6 kilogram meters squared per second. So it's just the total angular momentum is the vector sum of all the individual angular momentums. If we had 10 objects all rotating with their own individual angular momentums, the angular momentum of the system, we would just add them all together, just as we did with linear momentum.